SwayamPrabha. Digital India. Educated India.
Now, of course, we are not happy with just that, right. So, of course, we want quantum FHE, and this is a really nice space which has some very nice results. What is the goal here? So, what is the goal of fully homomorphic encryption? We saw a classical FHE in class. That is exactly right. So, we should be able to compute any quantum circuit. So, that means if I am given an encryption of some mixed state rho, then I should be able to compute any arbitrary quantum circuit on it. So, any unitary transformations, and we have seen unitary transformations that are complete for quantum circuits, right. So, we will go over that again, but basically like we have seen a Toffoli gate and a few other gates are complete for quantum. So, if we could find a way to apply these gates while the quantum state is still encrypted, we will evaluate quantum circuits again using a QOTP and now a classical FHE. So, similar to the PKE construction that we saw, we will use a one time pad and an FHE for the OTP key, alright. But we have to be very careful. So, there are a lot of things to think about. Let's sort of try to develop these ideas slowly. So, we have a QOTP of rho and some FHE encryption of AB, which is the secret key of the QOTP. So, let me write it as AB rho. Now, let's as a warm up let's think of evaluating a Z gate. So, now I have something like this, right. So, I have x to the a z to the b rho and then x to the a z to the b conjugate. I have something like this, and I have an encryption of AB. Now, say I want a ciphertext for Z rho Z dagger. So, what could I do? Very good. So, that is exactly the idea. So, we are just looking at this as a warm up, right. So, I already have this QOTP, again let us call it rho prime as before. Now, if I simply change this to an encryption of A and B plus 1, then what happens? The same rho prime, right, which is x to the A, z to the b rho, x to the a, z to the b dagger, right. This can be written as x to the a, z to the b XOR 1, z rho, z dagger, right, z to the b XOR 1, z dagger, x to the a dagger. Maybe I will put these. Do you agree? So, in this case, in fact, I am saying that we do not even have to change the quantum part. If I simply change the classical part, okay, the quantum state will get decoded differently. It will get decoded as Z rho Z dagger instead of rho. Okay, and it turns out that a similar idea works for other poly gates, for instance for X. Okay, and this is because these poly operators, they anti-commute. So, basically you know, xz will be equal to minus zx. So, even if I want to upgrade rho to, you know, x rho x dagger, then also I can do the same trick. And remember that global phase changes do not matter for quantum, right, because we will measure in the end and it will not matter. Okay. So, for these some of these simple gates, it seems that simply changing the classical part of the ciphertext is actually enough. Okay. So, this is just a warm up, this is like the simplest possible example. But of course, you know, you want to support arbitrary gates. So, let us start looking at universal gates. Okay. So, what are the universal quantum gates? Well, there are you know, there are many sets of gates which we can say are universal. So, one set is the so called Clifford group of gates plus Toffoli. Okay, and what are these Clifford gates? Does anybody know? I mean, we have not studied them in this class, but does anyone know? So, basically you know, these are this is a group of gates that is generated by the Hadamard gate. The Hadamard gate, the phase shift gate. So, this is the phase shift gate which we have seen before, okay, and the C naught gate. And this includes, for instance, poly gates X, Y, Z. Okay, so, this includes poly gates. And among the poly gates, you know, we saw how to handle X and Z, for instance. Okay. It will turn out that Clifford gates, all of them, have a nice property which allows us to handle Clifford gates in a very natural way. So, it will no longer suffice just to update the classical part of the computation, we will have to get into the quantum part, but it turns out there is a very simple transformation, okay, that will help us to handle the Clifford group. And having handled the Clifford group, we need to then worry about the Toffoli gate, okay, and that will be the rest of what we need to do. So, let me tell you what is the property of Clifford gates that we will use. For all x z, there exists an x prime z prime such that for any you know, state psi, c of x to the x z to the z of psi is equal to x to the x prime z to the z prime c psi, where c is a Clifford gate. Okay, so this is just a fact. So now this is really useful, right? So now can you think what we should do? If I want to apply this gate C to my ciphertext, then any idea what I should do? So I have my rho prime, right, that is my QOTP of whatever my state rho. Okay. Now I want to apply C to it. So I have rho prime which is QOTP AB rho, okay, and I have pi dot CT AB, right. This is what yeah, what I have. Maybe I'll change this to little x and little z to be consistent with the notation above. So I have this. Now, okay, so I claim that if I compute C rho prime C dagger, then then this is good, I claim. Why is that? So C rho prime C dagger is what? So it is x to the x, z to the z, small z rho, okay, x to the x, z to the z dagger, right, C dagger. Does everyone agree that this is what I get? This is just by simple substitution. Now, by the property that I have, right, I can write this as x to the x prime, z to the z prime, C rho C dagger, x to the x prime, z to the z prime dagger, by the property that we stated. Okay. So, this is what I wanted, right. So, now I can simply update pi dot Ct x z to pi dot Ct x prime z prime. Okay. And I could do all of this publicly. I do not need to know the information sitting inside the ciphertext in order to carry out this operation. That is quite important, right. So, there has to be a universal transformation that takes me from any x y to its corresponding x prime z prime. So, you are right that this going from x z to x prime z prime cannot depend on x z. So, like we saw in the case of the z gate, right, that we want to apply the z gate, it suffices to simply XOR, at that time we were calling it B with 1. So, this does not depend on what is the value of B, you just have to XOR it with 1. So, that is a very good question. So, this cannot work if this transformation depends on the underlying values. It is a very good question. Okay. So, this is great because we handled Clifford gates. Okay. So, now we want to handle Toffoli gates. Okay, and in order to handle Toffoli gates, I want to first define a cryptographic primitive called trapdoor claw free pairs. And in particular, we are going to look at trapdoor claw free function pairs. Okay. So, a TCF function pair is a pair of functions f0, f1 such that both are injective and have the same image. It is hard to find a claw that is some x0 x1 such that f0 x0 is equal to f1 x1. Okay. But can find it using a trapdoor given any y in the image. So, let us understand what this primitive means. So, this is a purely cryptographic object. Okay. So, it's saying that you know, we have a pair of functions such that the functions are injective and they have the same range. So, injective will mean that any point in the range there has only one inverse, right, and it is hard to find a so called claw, which means that you know, 2 points that take the 2 functions to the same output, 2 inputs that take the 2 functions to the same output. It is hard to find that. Okay. And this is in general hard, but there is a trapdoor that lets us do it. So, if I have there is some kind of trapdoor. Okay. If I have that trapdoor, then for any point in the image, any point y, I will be able to find x0 and x1 such that f of x0 is equal to f of x1 is equal to y. Okay, this is the definition of a trapdoor claw free pair, and we will see that this is very useful. In some sense, what can happen is, you know, we have seen these ideas of doing partial measurements and getting a superposition, you know, over points that somehow map to the same point, very high level, right. So, here also we will be able to somehow create a superposition over these claws. We will see how to do that. Okay. We will be able to create a superposition over the claws, but when we measure we can only get one of them. So, we can't get both of them. So, this gives us some kind of hardness for quantum adversaries. This is all very sort of high level, but I am just trying to give an intuition. So, we will see how to use this tomorrow, but at least the definition is clear, right. Good. Are there any questions? So, we only have 1 minute left. So, let us stop here. Are there any questions?